Hey guys, Steve here from Vorsprung Suspension in Whistler. Welcome to the Tuesday Tune. This week I'm going to have a chat about leverage rates, which is the leverage ratio change on the rear end of your bike. So all bike suspension frames have some form of mechanical advantage from the rear axle over the shock, with the possible exception of the old mandatory frames that literally had a fork attached directly to the rear axle in place of seat stays. However, most frames have some sort of leverage system that means that the rear wheel moves further than the shock. The ratio of these motions, how far the rear wheel is moving relative to how far the shock is moving, is known as the leverage ratio. The leverage ratio can be expressed in one of three different forms. Your overall leverage ratio, which is your total amount of travel divided by the amount of shock stroke that you have. So if you have, say, 8 inches of travel and 2 inches of shock stroke, you would have a 4:1 leverage ratio. You can express it as an instantaneous leverage ratio at any point in the travel, which is very handy, or you can express it as a leverage rate curve. And that is basically a plot of the instantaneous leverage ratio at each point in the travel. And the reason that that is particularly useful to know is that it gives us a very good idea of how a bike is likely to feel, what sort of characteristics it's going to have, and how it will behave with different forms of shock. So different forms of spring, different forms of damper. So here we have my amazing sketch of the rear end of a very simple bike. This blue thing being the swing arm, possibly of an old Alex Morgan BCD downhill bike from 2001. Obviously this is your rear wheel, which has been hammered by Aaron Gwynn down Leogang without a tyre. In this case we have 450mm between pivot and rear axle, 150mm between the shock eyelet and the pivot. So neglecting the change in angle here of the shock relative to the swing arm, we have a motion ratio, a leverage ratio of 3:1. So that is where the leverage ratio concept comes from. Rear wheel is moving 3mm for every 1mm that this moves. So key thing to note here is that as you alter this leverage ratio, and this applies both as an overall leverage ratio and an instantaneous leverage ratio, the effect that that has on the spring rate and the damping rate when measured at the wheel, which is all we really care about. We don't really care what the shock is having to generate. We only really care what that translates to at the wheel. As we alter this leverage ratio, you alter the damping and spring rates at the wheel as a square function of that change in leverage ratio. For example, if you took this from being a 3:1 leverage ratio to a 6:1 leverage ratio, for the same amount of travel at the wheel, the shock is now moving half the distance. But because the shock also has only half the amount of leverage over the pivot that it had before, so say we move this pivot into here, then the force that it generates through the spring and through the damper needs to be doubled as well. So we have it moving half as far and half as fast, but needing to generate twice the force at half the speed, or half the displacement. So what that means is that you would need a spring rate at the shock that's 4 times higher, and you need a damping rate relative to shaft speed that's 4 times higher as well. So this quadratic relationship between the leverage ratio and spring and damping rates gives us a very good idea of why bikes become quite sensitive to small changes in the leverage ratio. Okay, so on this graph we have a few different curves of leverage rate. So on this axis we have instantaneous leverage ratio. I have drawn that from 3:2. They're fairly common real world values that we'll see, meaning rear wheel is moving 3 times as far or as fast as the shock. Rear wheel is moving 2 times as far or as fast as the shock. Now the motion ratio that I've also included on the same axis is obviously the inverse of the leverage ratio. So it's basically, they're the same number, but one is dividing the shock travel by the wheel travel, one is dividing the wheel travel by shock travel. So obviously 1 over 3 is 0.33, 1 over 2.5 is 0.4, 1 over 2 is 0.5. So something that starts with a high leverage ratio or a low motion ratio and moves to a low leverage ratio or a higher motion ratio is considered progressive. The reason for this is that the effective spring rate and the effective damping rate for linear spring at, on the shock or a linear damper, they increase at the rear wheel according to where you are on the travel. This one here, with a completely constant leverage ratio throughout the travel, so no real change in that, would be considered linear. So when we talk about linear with respect to suspension, that can mean a lot of different things. A linear curve just means something that doesn't change gradient. Now, in the context of leverage rates, the consensus seems to be, don't shoot me, people from other bike companies that design these things and disagree. The consensus generally is that a linear leverage ratio is one that is constant. Although all these lines obviously look like straight lines, if you plot the spring rates at the rear wheel, this one will give you a linear spring rate, as in it's a constant spring rate for a coil spring. This will give you a falling spring rate, so the spring rate earlier in the travel is higher than it is later in the travel. And this will give you an increasing spring rate, progressive spring rate. So the spring rate at the start of the travel is lower, softer than it is later in the travel. Different bike manufacturers will use each of these in different parts of the travel. So what we end up with is curves that make use of all three of these aspects to suit the shock that they're working with, the use that they're going for. Now it is almost universally agreed upon that pure falling rates for rear suspension are pretty garbage. They are very stiff at the start of the travel and they are very easy to bottom out. There are only a handful of bikes that still use this. Usually it's paired with an extremely progressive rear shock, like an air shock with very low volume, in order to get the end stroke support that you need. Or it's used to overcome an exceptionally progressive shock like that. However, more complex leverage rates, like this one here, or this one here, are quite common. So now these are obviously almost inverted forms of the same thing. So the reason that I'm showing this is that something like this that starts off progressive and then becomes more linear and then digressive at the end of the stroke allows you to have something that is, relatively soft at the start of the travel, good bump absorption, nice and plush, and then doesn't ramp up very hard at the end of the stroke. The rate falls away at the end of the stroke. This is something that is commonly used in conjunction with air shocks, again, that have quite a bit of ramp up, because running a low leverage ratio in the middle of the travel means you can get more support out of the middle of the stroke of an air shock, which is typically its weak point, without causing something to be so progressive that you cannot use full travel. Conversely, some bike companies, a lot of VPP bikes and a few others would use a leverage rate curve that is something like this. So it's falling rate early in the travel, then it is, again, relatively linear in the middle, and then it ramps up at the end. Now, what this does is it means this part of the travel here is quite stiff, because you have a very low leverage ratio, well not very low, but a low leverage ratio early on. Then you have something that's softer in the middle, and then ramps up hard at the end. Now, this is a very common characteristic of VPP bikes. The guys that design them presumably want them to feel this way. The one advantage that this does have, in my opinion, is that it gives you something that has very low sag if you're after something that climbs very well, like the climbing geometry of the bike is very good. However, the soft middle of the stroke is something that may or may not be desirable. Likewise, the progressive end stroke means that it ramps up fairly hard towards the end of the stroke. Now, something like this, the falling, linear, rising characteristic is pretty well identical to the spring curve, identical to the type of spring curve, I should say, that you get from an air shock. So air shocks are stiff at the start, softer in the middle, stiff again at the end. So something like that exacerbates the characteristics of an air shock, and then you get something that is particularly stiff, particularly soft, particularly stiff. Something that runs an inverted form of that, like this other green one that I first pointed out, however, overcomes the initial stiffness of the air shock, gives more support in the middle of the travel, and then prevents ramping up too hard. So something like that will typically give you a more supportive ride. So the scale of this really matters. If I change this this axis so that these points are now, instead of being 3, 2.5, and 2, they're now 2.6, 2.5, and 2.4, then we're getting obviously much smaller changes in the leverage rate, in the leverage ratio, sorry. So then you can have something like the Yeti SB66, which if you look at that on its own, looks like it has a really odd kind of squiggly leverage rate curve. However, the actual variation in there is minuscule. It is effectively linear for all intents and purposes. So anything with less than 3 or 4% alteration in its leverage rate, its leverage ratio over the course of its travel is a very linear bike. So remembering again the big difference between air springs and coil springs is that coil springs are very linear. That is, they have a very constant spring rate throughout their stroke. Air springs, that spring rate can vary immensely. In some shocks, it can vary by more than a factor of 10 from the initial spring rate at the very start of the travel, which very, very quickly drops in the space of a few millimeters, to something that is literally 1/10 or even less than the initial spring rate through the middle of the travel. So if you are trying to select a new shock, for example, for your bike, it's worth having a look at the kind of leverage rate that your bike has and understanding, should I be looking for a linear shock, coil shock? Do I need more support in the middle of the travel, start of the travel, end of the travel? And then selecting the most appropriate type of shock for that. A frame that doesn't have much support at the end of the stroke needs to get that support from the shock. Conversely, a frame with a lot of support at the end of the stroke will do better with a shock that isn't ramping up too hard, isn't making it too hard to use full travel. If we combine a very progressive spring system with a very progressive leverage rate, for example, you end up in the position where you run a lot of sag and it's very hard to use full travel. That can make things harsh in itself, as you basically run into a wall of spring force with very small amount of positive travel available. Anyway guys, that's about it for this week. Let us know any comments, feedback or questions in the comments below, and we'll do our best to respond to them. Till next week, see you then.